my head, I would have got it. I moved it to the right
Okay,
instead of the left.
so Q of t, your cosine function looks like this. Starts at maximum,
Right.
goes through cycles, all that stuff, right?
Yeah.
Cosine omega t plus phi, where phi is between 0 and 90 degrees. That's a horizontal shift of this graph.
Yeah.
Negative phi. So you're going to horizontally shift this somewhere between 0 and 90 degrees.
Right.
Okay, so you shift the graph over a little bit. Let's just shift over this much. So here's a peak. Well, that's actually getting close to 90 degrees. We'll just shift it over this much. Now we don't know what phi is. That's going to depend, but there's our phi, right?
Right.
That means this point's going to shift over to here. This point's going to shift over to here. This is going to shift over to here. And this is going to shift over to here. So you're going to have something like this. Right?
Right.
So what's going to happen? The driving voltage is going to hit 0 before the charge on the capacitor does. Okay? Now, we saw that in physics yesterday. Okay? We saw why that is. Just from the exponential approach, if we have a constant voltage for time and then reverse the voltage to negative, and then positive, then negative. Okay? You keep chasing the voltage.
Right.
And if you're chasing the voltage, when the voltage goes negative, your charge doesn't go negative yet. Okay?
Right.
It takes a while for it to exponentially decrease to the negative. Well, that's if you have a constant voltage, constant voltage, constant voltage, constant voltage. Now, it chases the driving voltage in a similar way, but it turns out, as we just proved by solving this stupid equation, okay, or stupidly solving this simple equation in my case, it chases it in such a way that the charge in the capacitor is a cosine, a shifted cosine function that reaches 0 after the driving voltage does.
Right.
Now, physically, that's very obvious. It should do that. Okay? Well, same thing happens with a spring mass dashpot system. You got a simple harmonic motion, but if you're trying to drive it with a drag force, the driving force will reach the 0, the equilibrium point, before the oscillator will. And both of those are physically not difficult to understand intuitively. Although in our physics class, we're just starting to understand circuits. So it's a little harder maybe at this point to understand circuits, but in many ways circuits are much easier to understand than damped simple harmonic oscillators. Okay? But they're both extraordinarily important in engineering, which is why we're studying them in these courses.
Right.
Okay? At least, right now everybody in the course is in engineering, so we gear it that way. Okay, we understand? Very important stuff.